Today we're going to begin by discussing solving absolute value inequalities. But to actually do that, we're going to take a look at a graph of this first. Now, you got to trust me on this, but if I go over 5, down 12, and then graph the graph, it's going to look something like this. All right, and if I was to pick 0, 0 as a sample point, it would actually work for this. I'd get -2 is less than 0, and I'd shade in this region here. Now, this tells me all the shaded region is part of the solution of this inequality. Keep that in mind as we go through. In order to solve absolute value inequalities, we have to isolate the absolute value first. So I will add 12. Then I'll divide by 2. And we've achieved the first goal, which was to isolate the absolute value. Now, you can't do algebra with absolute value functions. So you have to remove what's inside the absolute value in order to manipulate it. We notice that x plus 5 is within this function. Think about what absolute value means. Distance from 0. So the distance of whatever this quantity is could be a positive or negative distance. Doesn't matter. But what's got to be true is it's less than 6. So what's in here could be, like, for instance, a positive 4. Or it could be a negative 4 and still satisfy the inequality. So to remove the absolute value signs, what we're going to do is use that idea. We're going to say what's inside could be a positive or negative value. Again, this time what's inside is this expression x plus 5. And that's going to be less than 6. So now really I have two equations, or two inequalities, that I can manipulate. One being x plus 5 is less than 6, and the other being the opposite of x plus 5 is less than 6. Both are pretty easy to solve. Subtract 5 from both sides. I get x is less than or equal to positive 1. I can do my arithmetic right. Multiply by -1 to this side, flip the inequality. So x plus 5 is greater than -6, and subtract 5 from both sides, and I get -11. And if you notice, my graph kind of indicates this. Here's roughly an x value of -1. And here's roughly, or a positive 1, sorry, once again. And here's an x value of -11. So now we have to state our solution. Well, again, looking at our graphs, we notice these are all the numbers between positive 1. So here's a graph on a number line, if you will, and -11. Now to state this in an inequality, we say these are all values x between -11 and 1. And that's my solution. I can state this using interval notation by saying all the numbers from 11 to 1, not including. Notice that's not a point, that's interval notation, and I've solved my problem. Let's do the next example. Now, if we want to look at a graph similar to what we did before, we have to take and set one side equal to 0, so it kind of represents a y equals. So if I was to add that 5 to the other side, I have a plus 9 is less than or equal to 0. And this allows us to just kind of cheat and look at the graph. So I go over 1, up 9, put a little dot. And if I was to graph this, it would look similar to this function here. Again, pick 0, 0, plug it in, and ask yourself, is 6 less than 0? No. So I would shade actually to the outside of this. So notice I'm shading, or my solution for instance, is outside of this number and outside of this number. Let's take and solve this using the principles of the last problem. We're going to isolate the absolute value, which gives me a -9. We're going to divide by a -3, giving me a +3, but I flip the inequality, and I have an absolute value of x plus 1 is greater than 3. Again, this, to remove, I say what's inside could be positive or negative, and that's still going to be greater than 3. Got two equations to solve. X plus 1 is greater than 3, and the opposite of x plus 1 is greater than 3. In the first, I subtract 1 and get a 2. In the second, I multiply by a -1, giving me a -3, and I flip the inequality and subtract 1 from both sides and get x is less than -4. If you look at our graph, very similar. So I say, well, my shaded region really happens where I have the following values, where x is greater than 2 and x is less than -4 on a number line are my solutions. Since there's no intersection there, I can state this by either saying x is less than -4, or, it's important that you include the or, x is greater than 2. Or I can use interval notation and say if I go from -infinity to -4, that's the interval of a solution in union with to infinity. And again, that's interval notation. And there's my solution. Now we're going to take and move from there to inverse functions. And we've talked a little bit about this before. Notation for inverse is f. It looks like raised to the -1 power, but it's not, of x. We're going to talk a little bit about how they look geometrically and how they look algebraically. We haven't really talked the geometric, so we'll start there. Geometrically, inverse functions are symmetric over the line y equals x. So if this is my xy axis, line y equals x is this diagonal line here. So if I take and graph a function, for instance, this here, and that's my f of x, it will be symmetric to its inverse function over this line. So if I were to reflect this over, I would get a new function that looks something like this. And we're going to call that our inverse. So that's what a function and its inverse would look like. Okay? We could pick any point over here, and it will reflect over to a point like this. Now, what we're going to do is we're going to take and actually sketch the inverse of a function. So I'm going to draw something. I will put a point here, put a point, let's say, here, and put a point over here. Let's call it this. And draw a graph associated with that. So this blue graph is going to be my f of x. And I want to sketch the inverse of that graph. So again, if I'm going to sketch the inverse, it must reflect over the line y equals x, which is here. Now, I believe we just got done talking about symmetries. And we know if we have y equals x symmetry, we can state that if the point was x and y, let's do this again, the point were x and y, then its image point is actually going to be y and x. So basically, if I want to graph the inverse of this function, I figure out the x and y values and switch them, and that should be my reflected point. So this is the point -3 and 0. This is the point -2 and 3. And this is the point right here, 1, 2, 3, 4, and 1, 2, 3, 4, 5. Now, if I want to be fairly accurate and reflect this over the line, I just flip all the x's and y's. So instead of -3, 0, I have 0 and -3. And that's my image point of -3, 0. Instead of -2, 3, I go 3 and -2. And instead of going 4 and 5, I go 5 over and 4 up. Somewhere right around here. And then I connect those dots. And if you look, that's a pretty good representation of the reflection of the blue line goes to the yellow line. So it uses a concept of symmetry that we just talked about. So now what I want to do is I want to sketch the inverse of y equals x squared over the line y equals x. Y equals x squared we know is a parabola. I can take and graph that. So I have my general pattern of 0, 0, 1, 1, 2, 4. Go ahead and graph that. Again, these all have known x and y values. We just talked, point xy reflects over to an image point of yx. So if I were to take and do that, 1, 1 is still 1, 1. -1, 1 goes to 1, -1. 0, 0 is still 0, 0. 2, 4 goes to 4, 2. Like so. And -2, 4 goes to 4 and -2. So now if you look, the yellow graph is the graph of an inverse. However, one thing to note here is that this inverse doesn't pass a vertical line test. So we say this doesn't have an inverse function. So since the reflection doesn't pass a vertical line test, the function doesn't have an inverse. That is a function, if you will. In order for a function to actually have an inverse that's a function, the function's got to be what we call one-to-one. In other words, it's got to pass both a vertical and a horizontal line test. And that's an important concept. Now, we've already done this year already, but we're going to jump into a little more difficult problem. If we want to take a look at inverses algebraically, there's two steps. One, you switch the x and the y value, then you're going to solve for y. So here I have a function y equals 3/4 x plus 5. If I want to find the inverse first, I will switch the x's and the y's. So this becomes x equals 3/4 y plus 5. I'll now solve for y by subtracting 5. And then multiplying both sides of the equation by 4/3. And that is my algebraic inverse of the function. Let's do another one for practice. Again, I consider this one a little bit on the easier side. Switch the x's and the y's. Remember, f of x just is a y. Same thing. So I say x equals 4y cubed minus 20. Add the 20 to both sides. Take and divide by the 4. And in order to undo a cubed, I'm going to cube root both sides. Okay? And that's my inverse function. Could say this is that. Since y equals x cubed is a one-to-one function, it passes both a horizontal and vertical line test. We know the inverse would be a function as well. Let's move to the next problem. This is one of the more difficult inverse function problems. We're going to switch the x's and the y's again. So I have x now equaling 2y plus 3 over y plus 1. I have to get y by itself. Now the problem is I've got a fraction here and I don't want to deal with that. So I'm going to multiply by y plus 1 to both sides. This term will reduce out. This goes to xy plus x equals 2y plus 3. Now again, I want to solve for y. In order to solve for y, think about what we've done in every other algebraic problem when we want to solve for a variable. We get all those variables to one side. So x minus 3 is going to equal 2y minus xy. I need to get y by itself. The only way to do that in this case is to pull out a greatest common factor. And now, since I have y times this quantity, I can isolate y by dividing by the quantity of 2 minus x. And this is my inverse. Like so. That'll do it for today. Answer the following questions, put them on the form, and I'll see you tomorrow.